Imagine trying to punch a hole through 5 miles of solid ancient granite. For a long time, our best solution was a tunnel boring machine, a multi-thousand-ton subterranean factory that literally eats mountains. But even these giants have a weakness. When the rock gets too hard, the massive steel cutters don't just wear down, they shatter, turning a multi-million-dollar project into a total standstill. What if you could soften the rock before the machine even touched it? This is the story of China's world-first hybrid TBM, a machine that uses high-frequency microexplosions to shatter the impossible. To understand the breakthrough, we first have to look at how a standard TBM works. It uses a massive rotating cutter head, pressing against the rock face with millions of pounds of force. Small hardened steel discs are the teeth of the machine. They don't actually cut the rock, they create stress fractures until the rock chips away into pieces called muck. In extremely hard granite, these discs can wear out in just a few feet of progress. Replacing them means stopping the entire machine for days, costing millions in lost time. Granite is a nightmare for engineers because of its crystalline structure. It's incredibly dense and has high compressive strength, meaning it pushes back just as hard as you push against it. The friction generated by grinding against this rock creates temperatures high enough to soften the toughest alloys. It's a battle of attrition that the machine usually loses. This hard rock bottleneck is why some tunnels take decades to finish. But Chinese engineers decided to stop fighting the rock and started outsmarting it. The idea was radical. What if we combined the precision of a TBM with the raw power of traditional blasting? It sounds simple, but putting explosives inside a high-precision machine is an engineering paradox. This new hybrid system integrates a micro-blasting unit directly into the center of the rotating cutter head. It's designed to fracture the rock just milliseconds before the cutters arrive. The goal isn't to blow up the whole tunnel. It's to create a network of microcracks that compromise the rock's structural integrity, making it as easy to cut as soft limestone. Meet the world's first TBM blasting hybrid. It's a 100-meter-long mechanical beast that looks like a standard boring machine, but hides a high-tech artillery system in its core. At over 12 meters in diameter, it's larger than a 4-story building. But the real magic isn't its size, it's the synchronization of its internal parts. But how do you set off explosions inside a machine filled with sensitive hydraulics without blowing the whole thing apart? The answer lies in the precision of the microblast sequence. The face of the hybrid TBM is a masterpiece of mechanical engineering. It features specialized apertures positioned between the traditional disc cutters to allow for the blasting charges. Automated arms behind the cutter head inject precisely measured explosive charges into pre-drilled holes in the center of the rock face. This happens while the machine is still in position. The charges are arranged in a specific geometric pattern. This ensures the shockwaves travel outward, maximizing the fracture zone while minimizing the impact on the tunnel walls. This isn't a single Big Bang. It's a high-frequency sequence of micro-explosions, timed to the millisecond. Think of it like a rapid-fire piston engine, but with explosives. As the charges detonate, they create a shatter zone in the granite. These microfractures spread through the rock, turning a solid mass into a web of weakened material. Just milliseconds after the blast, the cutter head moves forward. Because the rock is already fractured, the disc cutters can easily peel away the weakened layers with a fraction of the usual force. Explosions create massive shock waves that could easily destroy the TBM's internal sensors and hydraulic lines. To solve this, engineers had to rethink the machine's entire skeleton. The machine uses a series of high-capacity hydraulic shock absorbers. These act like the suspension on a monster truck, soaking up the energy from the blast before it reaches the core. Many of the most sensitive internal components are floated on vibration-dampening mounts. This decoupling ensures that even when the rock face is exploding, the brains of the machine stay perfectly still. The main shield of the TBM is reinforced with high-strength, impact-resistant steel. This protects the internal mechanisms from flying rock fragments and the intense pressure of the blast. Standard hydraulic seals would fail under this kind of vibration. Engineers developed specialized multi-layer seals that can maintain pressure even when subjected to high-frequency oscillations. Sensors throughout the machine monitor the health of the shock absorbers in real time. If the vibration levels exceed a certain threshold, the system automatically adjusts the explosive yield for the next cycle. Once the rock is blasted and cut, it needs to go somewhere. The hybrid TBM uses a heavy-duty screw conveyor to pull the fractured granite away from the face. Because the rock is pre-fractured, the fragments are more uniform in size. This makes the muck removal process much smoother and reduces the risk of the conveyor getting jammed by oversized boulders. This allows for a continuous flow of material, meaning the machine doesn't have to stop as often to clear debris. It's a seamless transition from explosion to excavation. The results of this hybrid approach are staggering. In hard rock sections where a traditional TBM might move only 2 meters a day, this system can double or even triple that pace. This speed isn't just a number. It's the difference between a mountain railway taking 10 years to build or being finished in 5. It changes the entire economics of infrastructure. While the hybrid machine is more expensive to build and operate, the time saved on labor and equipment rental makes it far more cost-effective for massive projects. But there's no such thing as a free lunch in engineering. Subjecting a machine to constant internal explosions significantly reduces its fatigue life compared to a standard TBM. The shock absorbers and seals require much more frequent inspections and replacements. It's a high-maintenance beast that requires a dedicated team of specialized technicians. Engineers have to carefully balance the power of the blasts. Too weak, and you don't fracture the rock. Too strong, and you shake the machine to pieces. It's a delicate dance of physics. Historically, drill and blast tunneling was one of the most dangerous jobs in the world. Workers had to manually set charges in unstable tunnels. With the hybrid TBM, the entire process is automated and contained within the machine's shield. No human ever has to step foot near the active blast zone. The explosives are handled by robotic arms and triggered remotely. This shift from manual labor to automated precision has revolutionized safety in subterranean construction. This technology is particularly vital for regions with challenging geography, like the Himalayas or the Caucasus Mountains, where hard granite is the norm. As other countries look to expand their high-speed rail networks through mountain ranges, this hybrid technology is becoming the new gold standard for hard rock tunneling. The machine can also switch back to pure TBM mode if it hits softer soil, making it an incredibly versatile tool for long-distance tunnels with varying geology. We're already seeing the next evolution of this tech, with research into plasma cutting and high-power lasers to further weaken the rock before the machine arrives. As our cities grow, we'll need to move more of our infrastructure underground. These hybrid machines are the keys to unlocking the space beneath our feet. Next time you're zooming through a mountain tunnel at 200 miles per hour, remember the mechanical beast that blasted its way through the dark so you could see the light on the other side.